Welcome back to a new video lecture, and in this lecture we discuss a new topic, and it is related with the kinematic method. The previous lecture we already discussed the term static method, and we already did some problems also related with the static method. So when coming to this kinematic method, in this method actually we are using the principle of virtual work. Okay, using the principle of virtual work we work out the problems in this case. So actually what is the principle of virtual work states, if a system of forces in equilibrium is given a virtual displacement, if you given a virtual displacement, then the work done due to external forces, is equal to the work done due to the internal forces. So using that principle we work out the kinematic methods for the different cases. So our final aim is to calculate the collapse load and also the plastic moment. So using this principle of virtual work, we work out the problem, that is equating this work done due to external forces, which is going to be equal to the work done due to the internal forces. So it is mentioned clearly in this case, that is by equating the internal work done by plastic moment at plastic hinge to external work done by loads. And also one more thing you have to note down, that this kinematic analysis can be used for continuous beams, then also for the frames. Okay, so while doing problems you will get more clarity regarding how to apply these kinematic methods to the beams and also to the frames. So first of all we discuss about some of the cases related with the beams. So actually the principle behind this one is the principle of virtual work. Okay, if you are given some virtual displacement to a system, then the external work done equal to the internal work done. That's only condition. So this is the question. Determine the collapse load in the simply supported beam shown in the figure. So actually this load is not acting at the center at a distance of A from the support A and B from the support B. Total length it is going to be capital L. So that's a condition provided. So if you observe that if the load is acting over particular point, there will be some deflection will occur. So you can represent that one as delta. Okay, since bending moment is maximum under the load, the interior hinge will be under the load. Okay, so here we are going to consider the hinge is going to be formed under this load, and the collapse mechanism is shown with the virtual displacement delta, and here you can observe some rotation is also happened, that is theta 1 here and the support B theta 2, and you can also note down this theta 1 here and theta 2 in this way. So in this case actually there is only one plastic hinge. Why? If you take the redundant members, what about the redundant member in this case? If you observe a number of redundant members here, there is a reactions, so total number of reactions it is going to be 2. Then what about the number of equilibrium equation? That is also going to be 2, so redundant it is going to be 0. And if you add up that 1, that is redundant plus 1 gives the number of plastic hinge. So in this case only 1 is going to be plastic hinge, and which is provided at below the load which is acting. So if you consider the geometry such that in this case if you observe this triangle, that is if theta 1 equal to opposite side by adjacent side, then you will get A theta 1 equal to delta, and similarly if you apply here B theta 2. Okay, so that's the case. And okay, then you can write down this equation in this way, that is theta 2 equal to A by B theta 1. Then coming to the internal work done, that is if you are taking this value, that if the plastic hinge is formed at this point and this plastic moment, that is MP, you can represent that plastic moment as MP multiplied by the rotation happened, that is at this point theta 1 and theta 2, so theta 1 plus theta 2, and if you substitute the theta 2 value here, if you substitute those values, the equation will become in this way. And finally you can write down those equation, that is B plus A, it is going to be L, and you can write down this equation in this way. Then one more time regarding the external work done, you know that the force or load multiplied by the displacement gives that value. Then delta you can represent a theta 1. Since here also theta 1 term is mentioned, so you can write down in the terms of theta 1, and if you equate those values, the collapse load, it is going to be L by AB multiplied by MP, plastic moment. And if this values is this load is acting at the center point for a simply supported beam, that is A equal to B equal to L by 2, the value will become, the final WC, it is going to be 4 MP by L. So please compare this value with the case of static method also, whether you got the same value or any change in that value also. Okay, so that's a case related with the simply supported beam with a point load acting. Okay. Then coming to the next one, a propped cantilever beam is provided and a W load is acting at the center point. And if you take the conditions in this way, in this case also, if you observe, the hinges are forming over 2 points actually. Since there is a reactions vertical and here a moment is also here is a reaction. So total number of reactions, it is going to be 3. Then number of equilibrium equation 2 equal to 1 plus 1 gives 2. So total number of hinges, it is going to be 2. So one we provide here and the other we provided under the load. So if you apply the load if you apply the W load, there will be a deflection delta will occur. And if you substitute those values, that is in this case, in the internal work, you can easily calculate that MP multiplied by, here is a plastic moment is formed here. So MP multiplied by theta, and here MP multiplied by theta plus theta. So you will get this value 3 MP theta. Then coming to the external work done, WC multiplied by delta. Then the delta value you can substitute in this way. If you take this triangle or this triangle, the same value, that is theta is going to be the opposite side by adjacent side. So you will get the value for theta is going to be delta, it is going to be theta multiplied by L by 2. Okay, if you cross multiply, you will get theta multiplied by L by 2. And if you equate those values, you will get WC is going to be 6 MP by L. So that's a case for a point load acting at the center for a propped cantilever. Also, you can compare this result with the static method. Okay. Then coming to the next case. So in this case, determine the collapse load in a fixed beam. And in this case, 2 loads are acting and both the supports are fixed. And this point load is acting this 1.25 W, which is acting at a distance of 0.2 L from the support A, and from the support B, W is acting 0.25 L. Okay, so that's the conditions on the from this question you can understand. And here you have to apply 2 mechanisms actually. So actually, first of all, you need to understand how many plastic hinges will form in this case. So if you consider there is one reactions, here also one reaction, one moment. So total number of reactions 4. Then 4 minus 2 gives 2. Then number 2 plus 1 gives 3. So number of hinges will form in this case, it is going to be 1, 1, 2. And we consider under this load for one condition or one mechanism, and another we consider under this load. So total number of reactions is going to be 3. So 2 cases we consider. The first case we consider under the load the 1.25 W. What about the WC value is going to be get? So this is the condition, and you need to calculate those triangles, the similar triangle laws, and if you have to equate those values actually. So in this case actually, delta 2 value, which is going to be 0.25 L, and if you equate this from this triangle, you will get this delta 1 value is that is theta 1 equals delta 1 by 0.2 L. So that's the statement. And you also if you consider this bigger triangle, you will get this delta 1 value as with respect to theta 2. Okay, then the equation will become very easy to analyze. So that's why written in this way actually. So if you consider this triangle, that is theta 2 is equal to this delta 1 by 0.8L. The remaining distance you will take, the 0.8L. Okay, the remaining distance. And here you again take theta 2 is going to be that is delta 2 by 0.25. With the help of these equations, we equate these values. And then coming to the next equation, that is 0.2L theta 1 equal to delta 1. And it is also equal to 0.8L theta 2. Considering this one and this one. Bigger triangle and this small triangle. Then the value is going to be theta 1 equal to 4 theta 2. Okay, so that's the statements. Then the internal work done you can easily calculate. First of all, MP multiplied by theta 1. Then coming to this point, that is MP multiplied by theta 1 plus theta 2. Here theta 1 and here theta 2. Then here you have to consider MP theta 2, and if you substitute those values for this theta 1 for theta 2, if you substitute those values, you will get 10 MP theta 2. Okay, so that's internal work done. And if you substitute for the external work done, you will get the value as, if you substitute for the external work done, you can observe that 1.25 WC delta 1 plus WC delta 2. Okay, the corresponding loads is acting. Here the 1.25 load is acting. So 1.25 WC multiplied delta 1. Here the W is only acting, WC multiplied delta 2. Then very easily you can substitute those values. For delta 2 you can substitute this value. Okay, that's written here. And finally you have to substitute for this delta 1 as 0.8L theta 2. And if you substitute those values, this is your external work done. So you can take any terms. In this case, both internal and external work done in terms of theta 2. That's why we are considering theta 2. Or either you can take in theta 1 also. There is no issue in that case also. And if you equate those values, you will get the equation in this way. And if you finally you will get the WC value as 8 MP by L. So that's the final statement. For when you are considering the hinges provided at the 1.25 W load. Okay, that's a statement. And then coming to the next one, that is regarding the second mechanism. So in this case, the W, we are considering the plastic hinges provided at the W load. So the procedures are exactly same. So if you observe from here, you can observe that the 0.75L theta 1 equal to 0.25L theta 2. Okay, so you are considering this one and this one. Then if you calculate those values, theta 2 equal to 3 theta 1, and then if you compare these values, that is delta 2 and this triangle, that is 0.75L equal to delta 1 and this 0.2L, and you will get the delta 2 and delta 1. There is an equation. Then external work done you can calculate by 1.25 multiplied WC delta 1 plus WC delta 2, and then if you substitute those values in terms of delta 1, and after that you have to substitute this delta 1 as is 0.2L theta 1. Okay, the delta 1 you can substitute 0.2L theta 1. How you got that value? Delta 1 as 0.2L theta 1. You are considering this triangle. Okay, so only using those similar triangle laws you can easily calculate those values, and after that if you substitute you will get WCL theta 1. Then internal work done, that is MP theta 1 here, then MP theta 1 plus theta 2 here, MP theta 2. Then if you substitute those values you will get, and for this theta 2 you can substitute 3 theta 1 from already we derived those values as theta 2 equal to 3 theta 1. Okay, So 8 MP theta 1, and if you equate those values, you will get WC 8 MP by L. And in both the cases, the collapse load, both the values are going to be same. So both the mechanism will occur simultaneously actually in this case. So that's the condition for this collapse load, collapse mechanism for this particular question. Sometimes the WC value will vary, and we will discuss such problems in the upcoming lectures. So I hope the section is clear, and with this we wind up today's section. Thank you.